Assalamu alaikum and hello to everyone. In this video lesson, we will continue with chapter 6 of our syllabus. In this video lesson, we will cover the third subtopic as highlighted on the left. The objective for the subtopic is on the right of the screen. Now, the second gas-powered cycle, which can be used to model an internal combustion engine, is called the diesel cycle. The diesel cycle is the ideal cycle for a compression ignition engine. Now, the difference between a compression ignition engine and a spark ignition engine is that in a compression ignition engine, only air is compressed during the compression stroke. And only at the end of the compression stroke, diesel fuel is injected, producing the combustion process. Compression ignition engine can operate at higher compression ratio when compared to spark ignition engines. The PV diagram for a diesel cycle is shown in the figure given. From the PV diagram, there are 4 reversible processes involved for a diesel cycle. From state 1 to state 2 is the isentropic compression process. From state 2 to state 3 is the constant pressure heat addition process. From state 3 to state 4 is the isentropic expansion process. And finally, from state 4 to state 1 is the constant volume heat rejection process. Now, for a diesel cycle, there are 3 types of volume ratios involved. The first one is the compression ratio, V1 over V2. And the second one is the cut-off ratio, which is V3 over V2. And finally, the third one is the combined ratio, V4 over V3. Now, let us look at the working parameters involved for a diesel cycle at each of the processes. For process 1 to 2, which is the isentropic compression, the isentropic relationship equation for gases can be used to determine the required properties at each of the states. For process 2 to 3, which is the constant pressure heat addition process, the following equation can be used to calculate for amount of heat added during the heat addition process. For state 3 to state 4, which is the isentropic expansion process, like before, the isentropic relationship equation for gases can be used to determine the required properties at the respective states. And finally, for process 4 to 1, which is the constant volume heat rejection process, the following equations can be used to calculate for amount of heat rejected during the heat rejection process. Now, let us look at the performance parameters for a diesel cycle. Number 1, to calculate for thermal efficiency, we can use the following equation. We can also calculate the thermal efficiency using the equation based on the compression ratio and also the cut-off ratio as given in the notes. And finally, we can calculate the mean effective pressure using the following equation, just like in the Otto cycle. Now, the advantages of a diesel cycle when compared to an Otto cycle are: diesel cycle produces a higher thermal efficiency, diesel cycle consumes less fuel, and finally, diesel cycle or diesel engines is suitable for application with when large amount of power is required. Now, let's look at an example involving the diesel cycle. You can pause the video to read and understand the question properly. For step 1, please try to draw and label the schematic diagram for the cycle. If you cannot draw and label the schematic diagram, at least try to draw the PV diagram. For step 2, write what is required or equations based on the question. Number 1 is to calculate for the maximum temperature of the air, which we know in the diesel cycle is at state 3. Number 2 is to calculate the thermal efficiency. We can use either equation to solve for the thermal efficiency. Number 3 is to calculate the amount of heat added to the cycle. We can use the thermal efficiency equation to solve for the amount of heat added, since we have already calculated for the thermal efficiency previously. For step 3, determine the required properties at each of the state. At state 1, since the value for temperature is given in units Celsius, remember to convert it in units Kelvin. At state 2, since process 1 to 2 is an isentropic compression, we will use the entropy relationship equation for gases to find for the temperature here at state 2. At state 3, for a constant pressure process from state 2 to state 3, we can use the combined gas law to calculate for the temperature here at state 3, which we can see has solved for the first item for the question. Finally, at state 4, since process 3 to 4 is an isentropic expansion, we will use the entropy relationship equation for gases to find the temperature here at state 4. Remember that V4 over V3 here is the combined ratio of RV over RC. For step 4, substitute and solve for the required items. For thermal efficiency, since the compression ratio and cut-off ratio values are already given in the question, it is easier to solve for thermal efficiency using the following thermal efficiency equation. For amount of heat added, since net power output is already given in the question and we have already calculated for the thermal efficiency, we can solve for amount of heat added using the following equation. Now, as an alternative method, we can calculate the amount of heat added by calculating the mass first and then solve for amount of heat added using the following equation. So this is an alternative method to find for amount of heat added. Please do not hesitate to ask if there are any questions regarding this example. Now we have come to the end of this video lesson. We will continue with our syllabus in the next video lesson. The next video lesson, we will look at subtopic C 6.4, which is the dual combustion cycle. Thank you for your attention and have a good day.